Hello everyone. Today we are going to see about the limits of a function. Let us study the behavior of different functions using examples. The first example was the function f of x is x squared if x is greater or equal to 2 and x over 2 minus 3 if x is less than 2. We will treat this function where x is close to 2 but x is different from 2. So let us take some points from the right of 2 when we close 2 from the right side of 2. Let us take some points. When x is equal to 2.5, we will substitute in this x squared. F of x will be 6.25. When we close again to 2, we can take 2.1, then f of x will be 4.41. When we take 2.01, f of x will be 4.040, and 2.001, f of x will be 4.004001. When we take x 2.01, f of x will be 4.0040. You can approach like this, close to x. When we close x from the left of x is equal to 2, then we can take 1.5. F of x will be minus 2.25. When we get more close, 1.9, f of x will be minus 2.05. When we take 1.99, f of x will be minus 2. Much closer to 2. When we take 1.999, f of x will be minus 2.0005. You can continue like this. So now we can say from the right side, now we can say that as x approaches to 2 from the right, that means from the right side of 2, the value of the function approaches for from the left side. You can say as x approaches 2 from the left of 2, the value of the function approaches negative 2. So we can plot the function. This is our x, f of x, and 2 is our limit point. As we approach 2 from the right, our function parabolic, which is approaching 4. X squared, and when we approach from the left side of 2, the function is x over 2 minus 3, which is crossing and approaching 2, 2 and crossing -3. X over 2 minus 3, our function. So we can conclude that the limits of the function f of x as x approaches 2 from the right is different from the limits of function of x as x approaches 2 from the left. This is one property of a limit. In the second example, we will see another property of a limit. Our second example is f of x, which is absolute value of x over x times x squared plus 1, where x is near 0, but not at x is equal to 0. From this function, we can see that f of 0 is not defined, because when we substitute direct substitution, 0 over 0 is undefined, not defined. But f is defined everywhere except 0. So when we approach from the right of x is equal to 0, which is x greater than 0, f of x will be x squared plus 1. So the limit of the function of f of x as x approaches 0 from the right is equal to the limit of x squared plus 1 as x approaches 0 from the right, which is equal to 1. When we approach from the left of x is equal to 0, which is x less than 0, the function f of x will be minus x squared plus 1, which is minus x squared minus 1. So the limit of the function f of x as x approaches 0 from the left will be the limit of minus x squared minus 1 as x approaches 0 from the left is equal to -1. Here 1 from the left side, -1. We see that the value of the function is not defined at 0, but the limit of the function f of x from the right and from the left exists. This is another property of a limit at that point not defined, but from the right and from the left exists. This is another property of a limit. The third property of a limit is the function of f(x), which is x squared if x is greater than 2, and minus half x plus 5 if x is less than 2, and 1 if x is equal to 2, where x is near the point x is equal to 2. And when we approach 2 from the right of x is equal to 2, the limit of the function f of x as x approaches 2 from the right is equal to the limit of x squared as x approaches 2 from the right is equal to 4. When we approach 2, from the left side of x is equal to 2, the limit f of x as x approaches 2 from the left is equal to the limit of minus half x plus 5 as x approaches 2 from the left, which is equal to 4. So, we can conclude that the limit of the function f of x as x approaches 2 from the right is equal to the limit of f of x as x approaches 2 from the left. But f of 2 is equal to 1, which is different from 4. This is another property of a limit. Now let us consider this function f of x, which is equal to root of 1 minus x near 1. You can see that from the function, the domain of the function is negative infinity to 1. Hence, we can't approach one from the right side. So, when we approach from the left of 1, the limit of the function from the left approach to 0. But we see that when we approach from the right of 1, the limit of the function doesn't exist. This is another property of a limit. When approach from the one side exists, from the other side doesn't exist. Consider the function f of x, which is equal to 2 to the power of x here. Our domain is all real number. And as we approach c from the right and the left, when we approach c from the left of c, the limit of the function f of x as x approaches c from the left equal to the limit of 2 to the power of x from the left equal to 2 to the power of c. When we approach c from the right of c, the limit of the function f of x as x approaches c from the right is equal to the limit of 2 to the power of x from the right is equal to 2 to the power of c. Similarly, for a greater than 0 and a different from 1, we can conclude the limit of the function a to the power of x as x approaches c from the right is equal to a to the power of c, and the limit of the function a to the power of x as x approaches c from the left is equal to a to the power of c. Limits of a function at plus or minus infinity. Consider this function 1 over x, where x is approach to infinity. As x approaches infinity, positive infinity, let us take some points. Let us take some points of x, 10, 100, 1000, and 10,000. When x is equal to 10, the function f of x will be 0.1. When x is equal to 100, f of x becomes 0.01. 1000, 0.001. 0.0001. When x becomes minus 10, f of x will be minus 0.1. Minus 100, minus 0.01, minus 1000, minus 0.001, 10,000, minus 0.001. So we can conclude from this table that the limit of the function f of x as x approaches to infinity is equal to the limit of the function f of x as x approaches to negative infinity approach to 0. Now we can plot the graph of the function. When you take positive higher values, we are approaching to 0. And when you take negative higher values, we are approaching zeros. For example, minus 0.1 at negative 10, and so on. So f of x is equal to 1 over x is, its graph look like this. So we can conclude that the limit of the function f of x as x approach infinity is equal to the limit of the function 1 over x as x approach infinity 0. Next time we will see infinite limit with examples, limit theorems with examples, and squeezing or pinching theorem, under continuity, asymptotes, vertical asymptote, horizontal asymptote, oblique asymptote, and two important limits, that is the limit of sin x over x as x approaches 0 is equal to 1, and the limit of 1 plus 1 over x to the power of x as x approaches infinity is equal to e.